Hey guys, so let's discuss position versus time graphs today. So here Mr. Fireman will help us understand position versus time graphs. Okay, so let's look at the simplest position versus time graph. Position versus time graphs are drawn to understand the position, the change in position and the velocity of an object and what happens to position, velocity, and acceleration as time goes on. Okay, so it makes it easy for us to visualize the motion of an object. So let's look at the simplest position versus time graph. Let's say Mr. Fireman over here is, so let's take this as our origin, x equals 0. Okay, so you definitely need an origin. So let's say that Mr. Fireman is standing at x equals 1 centimeter, right? And he's not doing anything, he's just sitting over there lazy. Okay, so what is the position versus time graph of this guy? Okay, it's just going to be a horizontal line. Okay, and this value is going to be 1 centimeter. Okay, so the equation for Mr. Fireman in this scenario is x equals x naught, right? Which is where x naught is just 1 centimeter. Okay, so this is the simplest position versus time graph. Now what if Mr. Fireman starts to move? Okay, so let's say he starts over here. Let's say he starts at x equals 0 now. Okay, then he moves to 1 centimeter in 1 second, 2 centimeter in the second, and 3 centimeter in the third second, 4 centimeter, and so on. Okay, so every second he's moving a centimeter. Okay, so the position versus time graph for Mr. Fireman now is going to be, so in 1 second he's over here, 1 centimeter, so that's the first point, and then at 2 seconds he is at 2 centimeter. Okay, and so on. As you can see that it's going to be a straight line. Okay, so that's the position versus time graph of Mr. Fireman when he is moving at 1 centimeter. He's moving at with a velocity of 1 centimeter per second. So he's moving 1 centimeter in 1 second. So that's his velocity, and that's the slope of this line. See, the slope is delta x over delta t. So 2 minus 1 divided by 2 minus 1. So in this case, the slope of this graph is the velocity of the fireman, which is 1 centimeter per second. And if you like SI units as I do, you can write 0.01 meters per second. So that's the second simplest graph. Okay, so the slope of the position versus time graph gives you the velocity of that object. Now you can see why these graphs are useful. So if the slope is fixed, you can see that there's just one position of the ruler, right? And I can just keep the ruler like that, and it just goes along with the line. So there's just one position of the ruler, which means there's one value of velocity in this case. Okay, now let's move a step further, and let's draw another position versus time graph for the fireman, right? Now in this case, what we'll do is the fireman will at x equals 0, Mr. Fireman is at at t equals 0, Mr. Fireman is at x equals 0, right? And then he'll move in 1 second, he'll be at 1 centimeter. In the second second, he'll be at 3, okay, at 3 centimeter, okay? And in the third second, he'll be at 6 centimeters, right? So you can see he's moving every second, the distance is increasing. So let's try to see what the graph, I'll just roughly sketch it. So you will get something like, okay, at 1 second, Mr. Fireman is at 1 centimeter, okay, x equals 1 centimeter, so that's your first point. In the second, there you go, sounds funny. No, I meant the second Mr. Fireman is at 3 centimeters. Sorry, there you go. So there you go. He's over here, not over there. So this is the second point. And in the third second, so 4, 5, 6, he's over here, moving fast. So in the third second, Mr. Fireman is over here. Okay. So you can see that the graph starts getting curvature, right? Like the graph starts turning, in other words, of course. Right? So what's going on is in 1 second, right? The first second he's at 1 centimeter, the second second he's at 3 centimeters, and the third second he's at 6 centimeter, right? So you can see that if you want to find the velocity, right? So you can look at the slope of this line will give you the velocity. So in the first interval, his velocity is 1 centimeter per second, right? And in the second, so you can see that this interval is 1 second, and this is, so the slope of this line will give you the velocity of the object, right? So 1 second and 2 seconds, right? So the velocity during this interval from 1 to 2 seconds, right, is going to be 2 centimeter per second, right? And if you look at the slope of this line, this is, I've squeezed it a bit over here, but if you draw it to scale, see that this will, you'll see some, see the slope of this line is of course greater than this, right? So it's going to be 6 minus 3 divided by 3 minus 2, right? The slope of this line, right? So you get 3 centimeter per second. So you can see that the velocity is increasing at 1 centimeter per second, right? So the average acceleration in this case is 1 centimeter per second squared. The acceleration is a fixed value, right? And you can see that if the time interval is really small, if I draw it carefully, it's just going to be it's just going to be a parabola. Okay, it's just you can see that it looks like a parabola, but not exactly. But when you draw it to scale and carefully, then it will look like a parabola. Okay, so notice that the acceleration is constant over here. Now, why is that the case? So let's go to the equations of motion. I wanted to first draw the graphs and then go to the equations. So the equations, you quite sure you've seen these equations. So delta x equals VIT plus half AT squared, and then VF equals VI plus AT, and then VF squared equals VI squared plus 2A delta x. And you can derive this equation from these two. If you eliminate time from the, take time and plug it into this, you get this equation. So anyway, so let's look at, so you can see that these equations, right, this is for constant acceleration. This is constant acceleration, okay? And you can see that this equation is just the equation, it's the equation of a parabola, okay? Because a parabola has, its equation is general equation y equals ax squared plus bx plus c, right? So this is just like, this is ax squared bx plus c, where c is the constant within this. This is x minus x naught. So this is just the equation of a parabola, and this is the equation of a straight line. So for an object moving with constant acceleration, remember this is constant acceleration. For an object moving constant acceleration, the position versus time graph is always going to be a parabola. Okay, always going to be a parabola. And the velocity versus time graph is always going to be a straight line with a slope. Okay, because the equation for this guy, the equation is just like y equals mx plus c. Okay, so that's why you see this this curvature over here, because I tried to move the fireman such that his velocity, right, changes at a constant rate, so that the acceleration is 1 centimeter per second squared, and then it starts becoming a parabola. It gets curvature. So acceleration introduces curvature in these graphs. If you see a position versus time graph with curvature, then it's always going to have some acceleration. Okay. So that was the position versus time graph, a basic introduction. Let's look at some examples before we stop. So let's look at this position versus time graph. So there's a position versus time graph, right? And let's look at this one. Okay. Now, what do you think? You can pause the video and think about it for a few seconds. What should the velocity versus time graph of this graph look like? Okay. So, if you draw the velocity versus time graph, remember these two are straight lines, right? And if you draw a straight line and it has a fixed slope, right, then it means that it has a constant velocity. Okay, slope of this graph is the velocity. If the slope is fixed, the velocity is fixed, which means that so if you trace the time over here, right, okay, the at this time, right, before this time, the velocity is a constant positive number. Constant positive slope means constant positive value of the velocity. Now, you should be able to predict what's the velocity, how does it change over here. So it's obviously going to go to the negative, because this guy has negative slope, right? It's like always, you can remember it this way: if you're going from left to right, if you're going up the hill, it's positive slope. If you're going down the hill, it's negative slope, right? So this is negative slope, and one value of slope means one value of velocity. So you get this. So that's the velocity versus time graph. And the acceleration versus time graph of this guy is going to be what? What do you think? So it's going to be 0, right? Except for these undefined points. These are not physical points, because we don't get a jump in the velocity physically, right? So this is undefined. Other than that, the velocity, where the acceleration of this guy is 0. Okay, you can have at this point there's a sudden change in velocity. That's it can be this. The function is discontinuous, so you're going to get a large value of acceleration. So I'm not drawing anything. I'm not going to draw anything over here. There's a sudden change in velocity, right? So these are undefined. In real life, these points don't mean anything, because it's a sudden change in velocity. So the acceleration for this guy, you can say is 0, except for this undefined point over here, okay, where the function is discontinuous. Now let's look at another position versus time graph. Let's say you have a position versus time graph that's like this. Okay. Now I intend to draw a parabola. Okay. Now, what do you think is the velocity versus time graph of this guy? So, what is the velocity versus time graph? Any ideas? You can pause and think about it. You should have your own prediction, so that you learn more if you have your own prediction, and if you're correct, you'll be happy. If you're not, then you will definitely learn a lot. Okay. So, the velocity of, now the ruler, you can see now the ruler doesn't have a fixed orientation. Every point you go, the ruler changes orientation. So at every point, there's a different value of velocity. Okay. At every point, you have to draw like a straight line, and and find the slope of that line. That's called the tangent. It's where the line touches the curve, right? That's the tangent. So the slope of the tangent will tell you the velocity at that point. Okay, so you can see that we start with zero slope, essentially zero slope, right? And then the slope becomes positive. The ruler is becoming more steep and steep and steep, which means the velocity is increasing, 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 increasing. And if this is a parabola, as I claimed, the slope, the velocity versus time graph is just going to be, so you start with 0, right? And then the slope is positive, becomes more and more positive. It means that the velocity is increasing towards the positive. Okay, so this is going to be your velocity versus time graph for this parabola. Now, if you have, let's say, a parabola like, let me just use light colors. So, if you have a parabola like this, right? You see that you, so this is concave down. So you can see that you start with 0 slope over here, right? And then the slope becomes negative, 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 because again, every orientation gives you one value of velocity. Okay, so and it becomes more negative, 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 negative. So you start with 0 slope, okay, and then it becomes more negative, negative. So the graph for the, oh, I should have used yellow. So the graph for that guy is going to be this line. Okay, that's for the yellow graph. Okay, so this is the green one. Let's call it 1. So mix the colors. Okay, this is the second one. Okay, so now if you want to plot the acceleration versus time graph of these guys for graph 1 and 2, what do you think? Pause and think. So this is a line with constant positive slope. Okay, so for 1 it's going to be constant positive acceleration. Okay, so this is your graph 1's acceleration. And for this guy, you can see that it's a negative slope. It's positive. This is negative. It's constant positive slope, or constant negative slope. You get this for graph 2. Okay. So that was. So I think this is it for the position versus time graph. A first introduction to position versus time graph. There's of course more to it. If you have any questions, post them in the comments. We'll discuss these concepts more in later videos, but that's it for now. Hope you liked the videos. If you did like it, press the like button, subscribe. See you later. Bye.